Hello, welcome to a actually discussion section today instead of problem. We are going to talk about Maxwell's distribution. It's a little bit advanced topic, and you can see from the integrals I've written on the right side. So what is this? Maxwell distribution is works with a model of a system. So say I have a system, gas, liquid, solid, whatever. Okay, so let's say gas, and it's got some molecules, and they're in motion. So each molecule can go in, say this is X direction, this is the Y direction, Z direction, can go in three directions. So if you have an atom, then you just have its motion, but molecule you have atoms combined together. So in case of molecules, you suppose you have a molecule like that, you look at the center of mass motion. Center of mass motion. So we can say kinetic energy of a molecule of mass m, say m equal to mass of the molecule. So kinetic energy of one molecule is half m its speed square. But this speed squared, I can if the velocity is in that direction, then you can do x, y, and z components. So this will be half m vx square plus vy square plus vz square. Now you can see all the molecules are moving at different speeds and different velocities. So you can imagine plotting their values in a so-called velocity space. So if you look at one molecule, maybe its point is there. So this is the velocity of one molecule. Some other molecule have this velocity, some other molecule have that velocity, some other molecule have that velocity. So this is velocity of different molecules. So if I Maxwell distribution is tries to connect these to the what's going on thermodynamically, temperature wise. So if you look at a small volume, so this point is Vx, Vy, Vz, and this volume is dVx, dVy, dVz. So Maxwell's distribution says a probability that if I pick a molecule randomly, that the velocity of a molecule in a system at temperature T degree Kelvin. Okay, so you can imagine the outside temperature is T and inside temperature is T, and it's thermal equilibrium. Velocity molecule is between Vx, Vy, Vz, so this components, and Vx plus dVx, Vy plus dVy, Vz plus dVz, okay, is so we can write down a function called v of Vx, Vy, Vz, dVx, dvy dvz, and so that's equal to, so there is a normalization constant here. I'm going to write now just a little bit, and e to the power minus, so kinetic energy of one molecule, so kinetic energy of one molecule over Boltzmann constants times t, dvx dvy dvz. And this, because there are three of these guys, when you integrate, and vx is from minus infinity to infinity, and so x, y, z is in this range, each one of them. So this is 3 of m 2 pi kBt. Okay, so this kinetic energy we already wrote down. You can think of that as this expression, and this is what is called Maxwell distribution velocities. So you can, if you want to convert this into a speed will be v, and you can see that if I drop it here and go in some kind of a spherical coordinate, this is say v theta, and v phi, I mean, and this angle can, let's call this phi in terms of v, and theta towards the v. So if you do this, and because kinetic energy only depends on the speed, for a speed it will just turn out to be the same thing, m over 2 pi kBt 3/2 e to the power mv square over 2 kBt 4 pi v square dv. And now this dv is 0, v less than infinity. So this is the speed, and this 4 pi comes from integrating over the entire solid angle. Okay, so this is we can actually compute a lot of properties using this. So let's compute one thing called what's the average kinetic energy. Okay, so kinetic energy, average kinetic energy of one molecule. Okay, so you can find out from here by doing averaging. So this is probability distribution, so half mv square f, let's call this this whole thing over here, let's call it fv, and then dv, I mean this include all of this, include all of that, anything other than dv 0 to infinity. This will be kinetic energy average, will be like that. And this is an integral you have to do. You can, let's write down this, so half m and this whole thing m over 2 pi kBt 3/2, and then 4 pi. An integral is going to be 0 to infinity. There's a v square there and there's v square there, so v to the power 4 e to the power minus m over 2 kBt v square dv. So that's where these integrals come in, and you can look up these integrals in an integral table. That's why I looked it up. So this now if you look at, compare this, the n is 4, so n equals to 4 in the integral table, and alpha is m over 2 kBt. That's the alpha. This thing is alpha in my table. So this and not 0 but even, so it's this thing. So this integral is simply going to be for r equals to 2. R equals to 2, that's 2 times 2, 4 minus 1 is 3, and this is double factorial. Double factorial, you skip every other term. So 3 factorial, 3 double factorial is 3 times 1, not 3 times 2. And then 2 to the power 2 plus 1 is 3, and square root of pi. And then you have a alpha, which is this whole thing, alpha to the power. So this is 4 plus 5 over 2. And this one is using alpha only. So this will be alpha over pi. So you can see alpha 3 over 5. You can a lot of things cancels out. So this guy cancels the entire thing and just becomes alpha. 3 over just 1 alpha left. There is a pi and it's got a pi. This cancels this pi with this pi, so all the pi's got cancelled, and you have 4 here and 8 and 2. So what do we get? We get 4 times 3 in the numerator over there, and then have 2 times 8, we get a 16, and then we have 1 over alpha. So 3 over 4 times, let's put what alpha was. Alpha was this 2 kBt over m. So 2 kBt over m, and there was this m over here which should have carried over here, and so, and this m got cancelled out. So this is equal to 3 over 2 kBt. So kinetic energy of one molecule. Now if we have n molecules, then kinetic energy of all molecules just going to be sum of this 3 over 2 n kBt, and this is the same as nr, little n, and the gas constant, so 3 over 2 nRT. So you can see that formula you can derive using Maxwell's distribution. You might say, where does this come from? You might say it's a gas, and using this gas we can actually derive this. Okay, so this fundamental way of looking at what would be. Now if you just have ideal gas, right, then there is no other kind of energy. There's no potential energy, no nothing like that. So if in ideal gas, the entire internal energy U will be just kinetic energy total. So the ideal gas U is going to be 3 over 2 nRT. Now monatomic ideal gas, there's no other kinetic energy. If you have a diatomic ideal gas, then you can have a rotational kinetic energy, and then in the vibration kinetic energy, but on top of this, right? So you'll have a center of mass, kinetic energy, what would, this is the center of mass kinetic energy. As you go back, we just look the center of mass movement. So if you have multi, not monatomic but polyatomic molecule, then you'll have in addition kinetic energy associated with rotation and vibration. But we haven't really done that here. So in Maxwell's distribution, you're only looking at kinetic energy associated with the center of mass motion, and this is pretty useful. Okay, so for instance, you can figure out what is the average speed, for instance, of a molecule. You'll be surprised, like upwards of on room temperatures, more than 500. 500 meter per second. You can figure out. So how do we figure out, say, speed of a molecule? I'm going to illustrate that next. Okay, so we want average speed. So we want to average v. So this is going to be 0 to infinity v times fv fv 4 pi v square dv, and this fb is just we have alpha over pi to the power 3/2 exponential minus alpha v square. Okay, so in earlier calculation we had to do v square. Now we have a v, so we are writing this out: alpha over pi 3/2 4 pi 0 to infinity v cube e to the power minus alpha v square dv. So look up in the table, because this is an odd power. We are in this situation with r equal to, so r equals to 1. So r equal to 1, this is alpha to the power r plus 1, not that way, alpha to the power r plus 1. So this is equal to alpha over pi 3/2 4 pi, and we have r equals to 1 factorial 2 1 over alpha to the power 2. Okay, so we get here this 2 cancels, becomes 2. So we have a so this is 3/2 times alpha to the power 1/2, right? So this guy cancels that guy, and this is pi. So this pi will cancel all of it, becomes square root of pi. So this with this pi will be 1 over square root of pi. So 1 square root of pi times 2 times 1 over square root of alpha. So alpha was, if you remember, m over 2 kbt. That's the alpha for us. So 2 over square root of pi times square root of 2 kbt over square root of m. So if I didn't make any mistake, I'm not sure I've made a mistake. So we get a square root of 8 kbt over pi times m. So this is, I think this is correct. I just checked it. And we can also find V square average, which is, you know, when we did the kinetic energy, that's what we did, right? So it was like a 0 to infinity, V square, FV 4 pi, V square dV. So if we, and FV is the same thing. FV is alpha over pi to the power 3/2 e to the minus alpha V square. Alpha is that. All right. So doing this integral gave us actually three. You can have a 3 kBt over pi times m. I think there's no pi there. No pi there. No pi there. So you can see the average speed is quite different than when you square that, right? So if you want to do the square root of this, V square and then average, this is called RMS speed, RMS, or root mean square speed. And if I do the square root, I'm going to get square root of 3 kBt over m. Now there's another kind of speed people can get from here. So if you look at this FV, so if I plot FV versus V, it will go up. For instance, okay, so it's not 0 here, so it's go from some constant V equal to 0, some constant, this alpha over pi 3/2 here, but it's going to have some maximum, and then at V goes to infinity, this will go to 0, right? So where is this maximum? So this V is called V at the peak. And so if you take a derivative set equal to 0, you get yet another speed, okay? And this turns out to be square root of 2 kBt over m. So we have one measure of speed, another measure of speed, and third measure of speed. These are all statistical measure of what is the average speed in the gas molecules. Of course, this is very crude, but actually gives a pretty decent amount of information and quite reliable. Okay, you can use these formulas for studying when you suppose you make a little tiny hole and you have gas at some temperature T. At what rate the gas molecule will come out? So you can see it will come out if the speed, if in delta time T, all the molecules which have a, say, x velocity in the direction of the hole and come out. So you can use this as a measure of the speed for it to come out. So that's one use of it. It's called effusion, and you can check that in that website. There's much more description there. There are other applications, like say if this molecule is moving around, and then it's gonna, if it's moving here, it's gonna hit that molecule. If moving there, it's gonna hit that molecule and bounce off. So over here it has that much distance moves. Over here that much distance moves before hitting. So what's the average length that it moves before hitting another molecule? So this is called mean free path. And you can use this these speeds to figure out a formula for mean free path. And I'm not going to do this. You can go out and check that website to study more from those concepts. So this is concept of effusion and this concept of mean free path. I think I've been kind of trying to get through this. My aim is to get to the electricity and magnetism part as soon as possible. So I hope this would be the end of it. Maybe in the future I'll do some videos on kinetic theory, but tomorrow onwards I will do videos on electricity and magnetism. So hope to see you when you start to study electricity and magnetism. Take care, bye.